You know, it turns out that actually exponential functions even go on in the refrigerator. Here's a question I want us to think about right now. Suppose you have an icy cold refrigerator, which I wish I was in right now, and suppose the temperature was 34 degrees in there. Okay, now you put a soda can into it, so you go whoop, and there it is. And that soda can, of course, was outside for a while, so it was actually pretty warm. And in 5 minutes, the temperature of the soda can drops from 75 degrees all the way down to 65 degrees. Huge drop in just 5 minutes. So that's some serious cooling going on. And now we can ask ourselves, well, can you figure out a variety of things? For example, can you figure out what the temperature of the soda would be in 30 minutes? Could you figure out when the soda will be a particular temperature? Suppose you want to drink it exactly when it's 36 degrees. How would you go about that? So actually figuring these things out can be done using some basic physics principles. And in fact, you would use what's known as Newton's law of cooling. Newton was everywhere, by the way. He just made a fortune on cooling and calculus. You wouldn't believe it. Anyway, and his laws. He has all these laws, too. Anyway, so it turns out that his law of cooling is the following. The temperature after t minutes of an object that's placed in an environment where the environment has constant temperature, like, for example, your refrigerator in an ideal sense, can actually be found by just knowing a few things. First of all, you have to know the temperature of the constant environment. So we're going to call that A. So A just represents the temperature, for example, of the refrigerator. It's constant. And then you add T sub 0, which is the initial temperature of the object that you're putting in to this environment of constant temperature, and subtract off that constant temperature of the environment. And then you have E, raised to the power minus KT, where T is the time, again, in minutes, and K is some constant. Now, K is some constant that depends upon the object you're putting in. In this case, it's a soda. And so that constant is going to be depends upon, you know, the can. Is it aluminum? Is it plastic? Whatever, and so on. So actually, that constant is determined heavily by the object itself. So we don't know what that is. That's sort of a mystery thing right now. But if you want to find the temperature after t minutes, you plug into this formula, where this is the temperature of the ambient space. This is the initial temperature of the object. And K is this constant. So if you actually want to use this thing, you have to know all this information. Now, we do know, for example, that the temperature of the refrigerator, I told you, was 34 degrees. So this is 34. And we also know that the soda can initially, when it was put in, I reminded you, was 75. So in fact, we can actually fill in a lot of these things for our soda can example. And I would see what? Well, this number here I said was 34 degrees. Actually, I'm not going to put the little degree symbol there, but of course, these are degrees. Plus, and then I have 75, and I subtract off 34. So that's going to be 75 minus 34 is 41. So I have 41. And then I have e to the minus, but wait a minute, I don't know what the constant is. Shoot. Well, this seems now like we're in trouble, because if I don't know what that number is, I can't actually answer these questions. But there was one piece of information that we were given that we haven't used yet. We knew sort of one data point, because we were told that 5 minutes later, after we put the thing in, this thing cooled down to a nice frosty temperature of 65 degrees. So that means that this must satisfy the fact that when t equals 5 minutes, the temperature must be 65 degrees. Well, that gives us an equation and allows us to solve for the constant. So just knowing that one little data point, I can now figure out what k is and then answer the other questions. So let's actually input that. So we know that when little t is 5 minutes later, this temperature is 65. So what that tells me is 65 equals 34 plus 41 e to the minus, and that's 5k, because the time is 5. Well, notice that's an equation just in terms of k. I can now find that constant. It eluded me for so long. Now I've got it. So what would I do first? Well, first I'll bring this 34 to this side, and that gives me a 31. And that equals 41 e to the minus 5k. I'll divide both sides by the 41 here, and I see 31 divided by 41 equals e to the minus 5k. How do I solve an exponential of this sort where the variable is upstairs in the attic? I want to get it on ground floor, so I'll take the natural log. If I take the natural log, I see natural log of 31 over 41. and that equals the natural log of e to the minus 5k. And now, of course, I use the property of exponents inside of logarithms to realize that can be pulled out in front as a coefficient. And that's the whole point of taking logs, to bring that unknown down to the first floor. Now, when I do that, what do I see? I see the natural log of 31 over 41 equals, well, minus 5k times the natural log of e. But what's the natural log of e? Well, the natural log of e is just 1. So, in fact, that term goes away. So I see this just equals minus 5k. And if I want to solve this, all I've got to do now is divide by minus 5. So I see that k, that constant, equals the natural log of 31 over 41, all divided by minus 5. And we can plug that into a calculator and see what the value is. And it turns out the value is 0.0559 stuff. So that's the constant. Now, I haven't answered any questions yet, but I now have a complete formula that I can use. So all this work was just to find that mysterious constant that we knew existed, but we didn't know what it was. Now let's see if I can do some fancy erasing here. I'm going to try to do this. This is going to be sort of a little experiment on the fly here. You want to see the experiments, don't you? There we go. Oh, except I just threw away my constant, but I'll remind you what it is. Here we go. In fact, now I can actually insert that constant right into this value. And let me just do that, in fact, with a different color. That'd be sort of fun. So in fact, right here, this exponent is now become minus 0.0559t. See, that's actually that constant I put that in. And the minus sign is the minus sign from here. OK, great. Well, there's the formula. So now we can start answering questions. For example, the first question I want to know is, what will be the temperature after 30 minutes? Well, that says, what's the temperature 30 minutes later? So that's just T of 30. So I plug in 30 for little t, and what do I see? 34 plus 41, e to what power? Well, e to the power minus 0.0559, that's the constant we just found, multiplied by 30 minutes, so multiplied by 30. And you can use a calculator to actually compute that with the exponential function there, and you'll see 41.6 degrees. Does that make sense? Well, let's just think about it. It's very, very, very qualitative. It started off at 75. 5 minutes later, it was 65. So 30 minutes later, it should be even colder than that, and certainly it is. Notice it can't be too cold. What if I got an answer of 25 degrees? Could that make sense? Absolutely not, because remember, the refrigerator itself is 34. How could a refrigerator cool something even colder than the thing is itself? Not possible. So in fact, this answer at least seems reasonable. It seems within the realm of reason. OK, now I can ask another question, though. Suppose I want to drink it at the very moment it's 36 degrees. I want a real icy cold one. What would I do? Well, now I want to find the time when the temperature is 36. So I set this equal to 36, and I solve for t. So I say 36 equals 34 plus 41 e to the minus 0.0559t. And I want to solve that for t. So the first thing I'll do is bring this over to this side, subtract it. And so if I do that, I would just see a 2. And if I divide by the 41, I would see 2 over 41 equals e to the minus 0.0559t. So again, what did I do? I just subtracted 34 here. That gave me a 2. But then I also divided by the 41 to get me down here. If I take the natural log of both sides, what would I see? Well, the natural log of both sides would give me the following. Natural log of 2 over 41. And what would I have on the left? Well, I'm on the right. On the right, I would take the natural log. I'm going to do all this in one step. The natural log of all this, but that now comes down as a coefficient, and the natural log of e is 1. So in fact, repeating the steps that I did previously, I just see minus 0.0559t. So what's t? T equals natural log of 2 over 41, all divided by minus 0.0559. And you can compute that on a calculator, and you'd get 54.03 minutes. So almost an hour. Almost an hour I'd have to wait. And does that seem reasonable? Well, I mean, it seems at least within the realm of reason, because we knew that 5 minutes in, I was at 65 degrees. 30 minutes in, I was 41 degrees. So this has to be longer than 30 minutes, and certainly that is. So in fact, what would happen is, 54 minutes later, you would open up your refrigerator, have an icy cold one, and you're all set. Ooh, that's good. All right, try these and cool off.